In this section, we are looking at solving polynomial and rational inequalities. In this equation, we are looking at values for x that when I plug them in, I find that x times x minus 2 is less than and equal to 15. Now we're going to use a trick here, but in order to use this, you'll need to either use a graphing program or a graphing calculator. If I subtract 15 on both sides, the right side becomes 0, and now on the left side I get x times x minus 2 minus 15. Now what we need to do to the left side is plug this into my graphing calculator, or whatever calculator-based app you're going to use. Now in a graphing calculator, what you want to do is everything on the left side of inequality, plug that into your y equals and hit graph. So you see here, this is what the graph looks like, where I have x-intercept at -3 and 5. Now what was the equation when we solved for 0? It was all values less than and equal to. And if I look at my graph, where does my graph start less than 0 here for the x-axis? Well, I see at -3 on the left side, it starts at 0, and it goes all the way down until it hits its vertex and comes back up. It's still less than 0 until it hits 5, and it equals 5. So here in this graph better highlights all values that are less than or equal to 0. As you see here in this graph, it starts at -3. So I'm going to put a open bracket for -3 in my set notation. All values between -3 going all the way to +5, which is also equal to 0, so I'm going to have a closed bracket. So the solution here is -3 to 5 with open and closed brackets. So again, how we want to solve this is to set it equal to 0, plug in what's on the left side into our graphing app or calculator, and then look at the graph and see if, based on the inequality, is that less than or greater than 0. Now here in this one, note that it is greater than, not equal to, so I don't need any values that are going to be equal to 0. I need all the values less. Graph this, and I see here that I hit 0 at -3 and at 2. And again, I'm looking for values that are greater than my 0, my x-axis here. So if I highlight the values greater, I see that my graph starts at -3 here at 0, continues on until it hits 2, 0, but I can't accept 0. So I can't accept that value of 2, and then it goes up. So as you see here, all of my graph that is greater than 0. So if I were to transform this into set notation, I start at -3 with parentheses because I cannot equal 0. I'm going to just be greater than 0, going all the way to 2. And the reason why I'm stopping at 2, because 2, you see here, is an x-intercept. It does equal 0, so I can't accept that 2 value. Then I want to also take the values from 2 all the way to positive infinity, and that's why this is separated out here with the union, because of this x-intercept at 2, 0. Now here is a rational function we want to solve for this inequality. Again, we want to set it equal to 0. Lucky for us, it's already there. And I want to set the left side into my graphic calculator. I want to graph this left side. So as we look at the graph here, as I highlight all values that are less than or equal to 0, I see that my graph starts at -infinity. All those values are less than or equal to 0. And then it goes to -3. It does equal -3 because I am equal to 0. Now once it hits -3, it's above 0, so I can't accept that. And then it hits 1, which I can accept because 1 does equal 0, which I can accept. And then it goes all the way down towards the negative values. And then you see here on the top, it jumps right back up. Now what happens there? Now if you can remember with rationals, we have what's called an asymptote. Now as we look back at the equation here, I see in denominator x minus 4. We know we can't have a 0 in denominator. What would make the value of x make that 0? Well, that would be a positive 4. And if I look back in the graph, positive 4 will become my vertical asymptote. On the left side of these values here, I see it is less than 0. But on the right side, it jumps back up to positive. It's greater than 0. So here, my values stop at 4 because that's where I have an asymptote. And it never touched 4 because we never touch our asymptotes, so I have to use a closed parentheses.